Hi everyone, this is Gogineni. I'll be taking today's session on generative AI design patterns. I think the slide and the marketing material from Toronto Machine Learning Society says that I'm associated with Observe.AI. That is about a couple months back. Recently moved on to Cohesity. A little bit about myself. I've been in the machine learning generative AI space for about 10 years now, and since almost the beginning, before generative AI was coined as a term itself. And I've seen this pile up, like this wave startup and a couple of previous waves, like similar to generative AI. Obviously, not at the volume of this one, but similar waves come in the past and then move on. So this one as well, just trying to put a perspective and the way of looking at it that makes sense for a lot of people, that makes it easier to ingest new knowledge, that makes it easier to build mental models, and is what I'm calling generative AI design patterns in this presentation. We can get started with that. I'll start with so the talk track. This is what it's going to look like. We are going to start with the intent and need for such a mental model, such a thinking objective, and go over what it definitely goes into is building some ingesting some building blocks of which will help you form the basis of your understanding, and then on top of it, like joining these building blocks in different ways and everything to come up with patterns. We'll start off with the most common pattern, which is retrieval augmented generation RAG. After that, we'll go into a couple other patterns as well. There are more and more patterns which are emerging as the field of generative AI itself matures. We'll go over a couple more of those, and I'll pause at that point to take in any questions. And if we have time, we could go over more. But given 30 minutes, I expect that we'll be able to cover 2 to 3 patterns fairly well. So the intent and the need for this. And if you have any questions, feel free to post them in the questions chat and everything. We can get to them at the end of the talk. So the intent and the need of why such a picture, such a way of thinking and everything is needed. The design patterns and this approach has been adopted by the software engineering community, by cloud community, and by a lot of other fields that have matured over time. And this is the same thing that is being brought in, and we are seeing more search patterns emerge in generative AI field as well as the field matures. So the building blocks plus patterns kind of an approach offers a modular mental model. You form an understanding of few of the building blocks, and then to solve certain problems. So whenever a certain problem comes up, it's easier to find associate it with a solution pattern by mixing and merging the building blocks that you may already have. And also there are some best practice patterns that keep getting published in literature and everything that very often can be applied readily to certain problems that you see them. And also another thing that is happening is that understanding of ML and Gen AI is becoming as fundamental as cloud computing, and that knowledge was 10 years back, and internet knowledge was like 20 years back, and so on. So most recently, software engineers and even machine learning engineers, everyone is expected to know a flavor or at least a level of generative AI and machine learning as a beginning set of their repertoire itself. So, for example, about 10 years back, when deep tech ML AI companies were being started, the startups and all the likes, people used to hire like two roles. One was like founding engineer, responsible for the back end and the platform aspect of it. Another one was a founding scientist, who was more responsible for machine learning aspects of it. These days, that's not the case anymore. They are hiring one person, and that person expected to know the fundamentals of ML and generative AI as well. So this is becoming a default expectation in the market. That's one thing, and also it's to complete in like 5 years from now, most software engineers will be expecting to know some ML and Gen AI, and this approach just offers the easy way to ingest that knowledge. And also knowing more patterns, the more patterns you know, the more intuitive and easy the problem solving gets in this space. Let me start off now with the approach itself. It starts off with, like, effectively there are some building blocks that some of you may already be familiar with. I'll just go over them once again, but there are a few building blocks, and we need to understand the building blocks first, and then using them you can build and create these patterns that you can use to solve much more complex problems later on. So the first one I'll talk about is embeddings. So embeddings, many of you may be familiar, but I'll go over this again, is it takes in a unstructured data. Now, these are models, embedding models and everything are models that take in unstructured data. Of it could be like images, it could be text, it could be freeform text, it could be videos, audio files, and any such inputs, which don't have a well-structured representation by themselves. Their length could vary, their dimensionality could vary, and all that. And they finally put them, like try to condense that information into a dense vectorial representation. And that vectorial representation is called embedding, and the model that does this is called embedding model. So that's a fundamental concept and a fundamental kind of a model that is being re-leveraged at multiple places in Gen AI patterns and in Gen AI solutions. So that's one part of it. It does a lot of stuff. One thing, it converts this unstructured information into something that is easier for the models to for the machines to understand. At the same time, it also condenses the information. Fundamentally, what happens here is that if the embedding model, if it's doing its job well, two things that are similar on the dimensionality, on semantic similarity, it could be like a meaning similarity, any of these the similar ones fall closer in that latent space, and the ones that are dissimilar fall further apart. So that's the fundamental idea over here. And once we add that to something, a new kind of vector databases that are popping up to help with embedding operations, which are vector DBs. There are multiple ones of these that are popping up. The most popular ones have been like Pinecone from a commercial standpoint, and Milverse, and these for from an open source perspective. So these databases are popping up for the primary reason of running operations on embeddings. Like, once you have taken unstructured data and converted it into embedding, finding similar embeddings to a certain one within your database, finding like doing efficient nearest neighbor search and approximate nearest neighbor searches, and all these. So the indexes and everything that are being formed in these databases are vector based indexes that help run these operations much more efficiently than if you were doing them traditionally on other databases. So these two components have been there around for a while. For like embeddings has been around for more than 10 years, and VectorDB has been around for like 4 to 5 years. With generative AI coming in, the embeddings have gotten really good. And the other part is that the the biggest problem with a lot of the LLMs and these generative AI models has been their hallucination. Primarily their hallucination, and the second one being their knowledge cutoff date, which is they were trained up to a certain date, and after that they don't have any world knowledge beyond that date. So to solve for these two problems, the next pattern, which the pattern that emerged first in the generative AI space, has been like retrieval augmented generation. It effectively uses these two building blocks to create a pattern that effectively addresses, not completely, but lets you control the hallucinations, and at the same time lets your system get augmented with knowledge beyond its training date. The pattern is retrieval augmented generation, and it's the most common generative AI design pattern going out there. There are multiple tools and libraries which are coming up just to like do this pattern elegantly and at a enterprise scale in a safe way and all that. So this does the two things: augments the knowledge of an LLM and controls the hallucinations. There are two phases. There are two. So let's go quickly over this pattern so we can everyone is on the same page. There are two phases to this overall pattern. The first one, the one above the dotted line, is the ingestion phase. What happens during the ingestion phase is that the documents that you want to augment your LLM with, they are brought into the equation. They are first sent to the embedder. Like we discussed, the embedder's job is to take in these raw, unstructured text documents and convert them into embeddings. Embedding would be a representation of that each one of these documents. It takes them in, it converts the embedding. There are hundreds of embedding models out there which do the described job fairly well. So all of these documents are converted into embeddings. The next step in the ingestion phase is storing them onto a vector DB. And also, I'm just skipping some of the other steps, non-interesting steps over here. There is parsing that needs to be done. There is chunking and embedding and a lot of those things. But the idea is that you take in a document, get it into a representation that best represents it, and then store it onto a vector DB. This process is usually a continuous ingestion kind of a process. It keeps happening for most of the real world data sets. The embeddings keep flowing into the vector DB. They keep getting indexed and everything. And this is the ingestion phase. This happens in the background. The second thing, the second part, the second sector in this overall pattern is the query phase. This is where the user queries. Imagine a ChatGPT query or something that the user has put in. The query itself is again embedded into the same embedder is used in both these cases. So the user query embedding is in the same space as the document embeddings. And VectorDB support like queries like get similar documents, get similar embeddings, and such operations. So you run that specific operation using the user query embedding. What that does fundamentally is that you're searching, hey, I have this set of documents. Which documents are most similar to my user query? So the VectorDB then returns the documents that are similar to the user query. Those documents are now augmented to the user query, and the entire thing is sent in as a prompt to your LLM, and the LLM then generates a response. Which this entire pipeline, if we say this entire pipeline is RAG, then the response that the LLM generates is a RAG augmented LLM response. Why does this help? This helps because without augmenting the relevant documents into the overall query, the LLM has a risk of hallucinating things that it doesn't know. If, for example, in 2018, someone asked about COVID, like the LLM was trained up till 2018, but if somebody asked it about COVID or something like that, it would have no picture about, it would have no knowledge or no picture about that event even occurring. And there's a chance that one, it could hallucinate and give out some wrong information. And at the same time, there's also a risk that it will not give any information, which is again not very helpful. So if we add some documents and some news articles and all of that into the overall system of events from 2018 to 2022 or things like that, that usually augments you're providing that information to LLM, and you're leveraging the LLM's reasoning capability and its language capabilities, and not relying heavily on its knowledge and articulation capability. So it's just like you're choosing the parts of the LLM that it's capable for the specific task, and the other ones you're augmenting through different mechanisms. So that's this pattern in its essence, being used aggressively in a lot of use cases in the industry. This is the most common one that is going on. Wherever you see like knowledge-based searches, wherever you see like Google being replaced with these new answer engines and everything, like the likes of Perplexity and so on. This is the pattern that is going on in the background for helping achieve those use cases. So yeah, this is one thing. And this is the most common one. Let's move on from here to a few of the other ones so that everyone understands how to identify patterns and how to spot them and how to apply them to your own contexts. For doing so, we need to pick up a few more building blocks. These are let's start with this clustering. So clustering has been around for like longest while. This is one of the oldest traditional machine learning approaches. The idea here is you have a lot of documents. They could be structured, unstructured, or whatever. You're trying to group the similar ones together, while at the same time trying to like separate them from the ones that they are not too similar with. So if we run this on, let's say, on Wikipedia or something like that, you're expected to come up with the clusters representing each of the topics that are happening in the Wikipedia. So there are a lot of clustering algorithms, few that require you to determine like pre-announce the number of clusters that your system is expected to churn out, like k-means and a lot of variants of that. And there are also ones that try to come up with the number of clusters and dictate it based on the data itself inherently themselves. The likes of that are like DB scans and hierarchical clustering and all those, which try to do this in a completely unsupervised kind of a fashion without any hyperparameter tuning. Lots of algorithms here, but the essence here is takes in a list of documents, likely converts them to embeddings, not necessarily, but likely converts them to embeddings, and then clusters the embeddings into things that are common and and separates those clusters from the ones that it is dissimilar with. The other very interesting building block that is coming up recently is this. This is not an official term as such. Clustering has been in the textbooks for long enough, so you can put a formal name to it. But LLM agents is something that is coming up recently. A lot of folks are calling it differently in their own context. But the idea is that a large language model, you're leveraging a LLM mostly not for its language capabilities, but for its reasoning and instruction adherence capabilities. What we do over here is to a LLM, LLM is augmented with certain tools. The tools could be like calling an API, or it could be like generating a code. It could be a Python interpreter. It could be like a database so that it can query the database directly. So these tools are equipped with the LLM, and the LLM is expected to use, and the LLM is also given instructions on how to use each one of these tools if need be. And based on the user's inputs, the LLM is able to take actions. It's able to use the tool to generate the output and so on. The most common example that you may have seen this might be in ChatGPT's image generation capability, or ChatGPT's code generation capabilities, for example. So what's happening over there? It's taking in the user input, and it has been equipped with a tool of like image generator, which is again their internal model of DALI. But that tool that it has been equipped with, it is calling that tool with, it's figuring out, the LLM is figuring out the prompt, the input instructions, and the formatting and all of that for the tool. It's calling that tool, and the response of the tool is being used by the LLM again to give back the answer to the user. For example, if I say, hey, give me a picture of give me a unique picture of a cat. So that's a pretty simple prompt that I gave it. What does unique mean? There's a lot of ambiguity to it. So LLM comes up with an elaborate prompt. It could come up with the unique picture of a cat be translated into a cat with white spots on it with blue eyes or something like that, something more elaborate. And that is sent into the image generation model. So it's basically doing the job of being a wrapper between the actual tool and between me. I could give it something ambiguous. It knows what the tool can do, what format is it expected to work in, and everything, and gives me a natural language interface with the tools that it's equipped with. So these are two other building blocks that I'll just use to cover a few more patterns up next. Let's go on to the next one. Yeah, this one is the LLM agent itself. Is basically, it has tools, interacts with the user, and uses the tools to help the user out better. The state-based agent, which is one level above that, is effectively you're creating multiple such agents, and you're effectively drawing out a graph between them. So again, there are two phases to this overall pattern. The first phase is the graph building phase. What happens here is there is some admin user who is configuring the graph, who is building the graph and everything. In an enterprise context, it could be like like a power user, someone in a cloud context. It's similar to a DevOps, or someone who owns the cloud, so who owns the AWS platform, something who is creating the graph for your organization or so. So the admin user uses a graph builder tool. It's usually a simple drag and drop kind of a tool to basically chalk out these agents in a UI or in a intuitive kind of a way. The agents are then like linked to each other. Like, hey, you start out with agent 1, then you can stay in agent 1, or you can go to agent 2. Once your state is in agent 2, you can either go to agent 3 or agent 4, or stay in agent 2. You can't go back to agent 1, and so on. So effectively, this graph is defined, and each agent basically has the things like, hey, when should I go into agent 3? So the transition logic, some tool set. So each agent is equipped with a different tool set. That's the idea of state-based agent. If all the agents were equipped with the same tool set, with the same LLM and everything, then you could just have one agent, and it could mostly do the job similar to this one. The idea of creating multiple agents and linking them in a graph kind of a structure is that you equip each of the agents with like different tools and the likes of that. Why does this become useful? Because let's say you are building a chatbot or something and the chatbot is for flight scheduling and such use cases. Before you let the user even like change their flight details, you may want to verify that they are the right user. So you may want one agent at the beginning, which does the verification part. It checks with your internal information system. It asks the user for their date of birth, for their some identification information, and then validates it against your database. And then only when it has like given approval that, hey, this is the right person, this person is authorized to run these 4 actions, only then does it go to the next agent, which is actually allowed to run, which actually has the tools to run those operations like flight cancellation, flight booking, and all such things. So This is a safer pattern. It's basically like the pattern that came before this was like a dual LLM pattern that only had like two agents working in tandem, one with read access and one with read plus write access. This is just like extending it further to create like multiple states, and it could and a predefined graph that it could move through to answer the user queries. There's also that access IAM's preconditions, like before you come into the specification, these four things need to be checked off and things like that, that effectively define this graph and everything. And once this graph is built, it's straightforward after that. The user input comes up. This entire thing is considered like a state-based agent. It starts off, the state starts off in the first node or the first agent over here. And when the user input comes up, the agent takes a call that, hey, one, what should my response be? Should I use any tools? If I should use them, how should I use them? What input should I give the tool? And if our output came from the tool, how should I incorporate that into my response? And also internal state transition. How should I transition my state? If so, who should I transition into? At each state, it has a few options to transition a state. So which option should I take? So that's the essence of the state-based agent. This is used mostly in conversational agents where not similar to ChatGPT. ChatGPT is mostly risk-free chat interface, but more enterprise use cases where there's a risk involved. There's a risk of doing something wrong is pretty high. It could be with respect to giving a response. It could be with respect to like running a tool in the background when you're doing applications that require automation, that require like risky automation steps and everything. This is a great pattern to put like levers to control that and to prevent abuse of those and things like that. The next pattern that I want to talk about is something that, again, the same pattern emerging in multiple spaces with different names and everything. I'm just calling it cluster pulse, but you would see the same pattern emerging in multiple places. This pattern is being used for extract, like imagine the use case where you have lot of data, like lot of unstructured data, no annotations, no structure, no labeling, anything to it, just a lot of data in some form. It could be videos, it could be images, it could be text, whatever, but a lot of data. In such cases, this pattern automatically comes up with a taxonomy, topic model, and things like that, so that it's easier to navigate this data. So if someone asks the question, hey, what's going on in this data? What is in this data? How should I look at it? What all categories are there? Are there some comma, like what is the percentage of each one of these categories, and questions like that, and even deeper analysis than that. It gives you insights from a lot of unstructured data. So, and this is something that the analogy of this in the previous world was like topic modeling. That was the closest associated thing to this. But this is just like, you can imagine topic modeling on steroids. So what happens here is you have a lot of documents. This is your unstructured data set and everything. The first thing that happens is you send it through your LLM. The LLM takes in the focus criteria, like, hey, this is your entire data set. What dimension do you want your analysis on? So the dimension could be, hey, I'm interested in for example, if this is text documents or something, there's a lot of text documents, you're interested in the policies in these text documents. That could be a focus criteria. An alternative could be that, hey, I'm interested in like this, the semantics of this overall text documents. It could be that, hey, I'm interested in the finance jargons, only the finance parts that are being talked on in this text document set. So the area that you want to focus on. So that is like the LLM is used to summarize your entire document set using your focus criteria to churn out anything that is not in your focus criteria. The idea is if you are doing your analysis, if you want insights on one dimension, your data may have like 100 dimensions. Let's just churn out the, let's take out all the ones that that we are not interested in at this moment and only leave the ones that we are interested in. The idea of that is to, for the remaining part of the pipeline, it makes it much cleaner. So that's the first step. You take in a focus criteria from the user. If they don't give any focus criteria, then the LLM just does a plain summarization. This is an optional step, helps with like focusing on one aspect rather than like going blind into your analysis. Once this is done, the next step starts with embedding that we looked into earlier. All of these documents, they go through the summarization focus criteria and then go into embedder and come out as representations. Each one of this gets a representation. And once you have the representation, The clustering, whatever, you can use any clustering algorithm over here. The clustering algorithm is run to put these representations and effectively the documents into various clusters. The clustering algorithm, if you know like what kind of what is the rough number of clusters your data may have, you can use k-means, but that's not usually the case. The usual case is you don't know what kind of data lies, how many clusters may be there, how many, what is the weight of each of the clusters and all such things. So more algorithms like db scan, hdb scan and such things are used in this as a clustering algorithm in this regard. Once you have the clusters, the next step is something like cluster analyzer. What it does is it effectively gives analysis for each of these clusters. For example, the simplest analysis is just like, what is this cluster talking about? And to do this, you can just send few of the data points, the original data points from this cluster to a LLM. And the LLM will effectively, you can use the LLM to summarize that to like 2 words or 3 words and give a name for that cluster. So the simplest thing is when you run it through LLM, it can give a name for each of these clusters. So you understand like overall in this document set, these are the topics that are being talked about, and these are the documents in each of the topics. So right at that point itself, it starts giving out value, but you can get more analysis out of it. You can like elaborate descriptions of these. You may want to like come up with questions for these. You can have the LLM do that. And non-LLM based analysis, like if you have metadata associated to each of these documents, then you can run SQL queries and all those simple any kind of other queries on your metadata to come up with the average. For example, if these were finance documents, the average value of like tax in this cluster was this amount. The average value of tax in this cluster was this amount, and so on. So it allows you to run a lot of analysis. Some analysis that if you some voice of the customer kind of analysis, which is tell me what I don't know, which the LLM will automatically churn out. But also a few things, if you know what you're specifically looking for, then you can use this pattern to get that exact information with much more efficiency than you would if you started off with the document set wholly. So yeah, that's all I wanted to like share in this presentation. The idea here is that there are patterns emerging, there are building blocks that are emerging. This is a great way to look at it. This is a great mentor. It helps looking at it this way helps easier ingestion of information with so much information coming out. It helps with easier information. Whenever you see a new version of the same thing, you can just like tag it as cluster pearls and then just like form your basis on top of it, rather than like treat all of these ones as separate information and separate models and separate architectures and so on. And similar approaches have happened in like cloud computing and as well as in internet era when those waves happen, and even within machine learning in automatic speech recognition world 5 years back and so on. So when there is a wave that's happening, a lot of information is usually churned out, and finally, after the wave is over, it usually stays out. Such patterns and few building blocks are what remain. So yeah, this is like we can start identifying them and tagging them during the wave part itself to make it more efficient for everyone. And that's it from me. Let me, if there are any questions, would be happy to take them. Okay, let me just, I see a lot of questions. I'm just looking at these now. Let me go quickly over that. Does RAG then increase the token size since you're sending the documents as well as, yep, RAG does increase the token size. So the idea of RAG is that your token size increases, your context window and everything, so is needed to be higher for RAG to be enabled. What you're trading off here is instead of fine tuning the model with all this information, you can alternatively also take the same document set and fine tune your model and hope that it will learn those aspects and get better at it. But that's the cost that you're eliminating. So you're taking off that huge one-time cost at the expense of a recurring small-time token increase cost. And for a lot of the use cases, it actually makes sense. And as the document set keeps changing, if your document set is constant, I'll like lean more towards like fine-tuning your LLM. But if it's not constant, if it keeps getting updated, if new information, if the recency of new information is really important for your use cases, then RAG really shines in that case. Yeah, you mentioned that Perplexity and other AI sessions. Can you please break it down? Yeah, so let me just give the example of Perplexity. So Perplexity, the document set in Perplexity's case is the internet. Like they're not indexing on the entire internet. They are indexing more on like reliable sources from the internet. for example, Wikipedia, few Reddit subreddits, and few other places that like Medium and such things, which are more reliable. So those parts are similar to how Google indexes all of these into its page rank algorithms and everything. Perplexity and such similar search answer engines are like indexing reliable sources in the internet into their vector DBs. And whenever a user query comes in, the same RAG pattern is run over there. So the documents from the internet which match best with those are retrieved. Those are sent to LLM, and the LLM then streams the response which is shown back to the user. So effectively, RAG, it's a streaming kind of a RAG, but yeah, that's what is happening over there. And they have like these crawler, very similar to Google, but imagine instead of when the user query came in, first of all, the documents aren't on these traditional databases, they also are on vector databases. And when a user query comes in, it's also taken to the embedding space, and then the RAG pattern is running there instead of Google's page rank algorithms. Yeah, I think we should have a recording for this. The TMLS team will just like share it right after the session. So for state-based agents, actually state-based agents is the one for which there are not a lot of frameworks which have emerged as of now. But the simpler version of it, which is like dual LLM pattern. So that's something that was like coined about 1 year back, and there are like there are frameworks in LangChain as well. There's a library for that which allows you to implement that. LangChain is the most common one. Most of the patterns that I just mentioned, they are popping up on LangChain soon. So the dual LLM pattern is already present. The state-based agent is also like on the roadmap over there. Is cluster analyzer an LLM agent? Yeah, cluster analyzer can be an LLM agent, but at the same time, it can also like be like SQL queries. It could be like fixed. If there is metadata available to documents, then it becomes really powerful. You can use simple queries. You can write simple custom functions if you know what you're looking for. If you don't know what you're looking for, in that case, just giving it to LLM and like asking it to, hey, name this cluster. Hey, give me a description of this cluster. Hey, give me few keywords that I can use to represent this cluster and things like that. That itself like tells you what gives you a good starting point. But usually in my experience, after that point, you take the control and then you start asking explicit questions, or you start like, if there's metadata, you like write custom queries to get to more fine answers. And the Bercy is asking, can we see some examples where a layperson might see these patterns? Are these a default at current or an enhancement of premium? RAG is custom. Like RAG is kind of like custom GPTs where you're creating your. I'd say that custom GPTs has a RAG component to it, but it also has some other components. Like it allows you to add like few tools that they provide and things like that. But there is that knowledge base part, right, where you can upload your knowledge documents when you're creating a custom GPT. That part is the RAG part in the overall custom GPTs part of OpenAI. And these patterns, like you will see these emerging. RAG is the most common one. There are like companies coming out to be RAG for for finance professionals, or RAG for lawyers, which got pretty famous too, like Harvey, Butler Labs, and those companies. There are multiple companies emerging with RAG. Few ones are emerging with state-based agents, which are like, I can share a few names like Sierra, Emma, and these are few companies which are leveraging with the product around these patterns. They're mostly targeting like voice bots, customer service in these industries at the moment, but the idea is that they will expand into other use cases as well. And cluster pearls and so on, that's a less explored thing. There are papers emerging in that space, but there isn't a lot of companies and those things emerging. But you can identify that straightforward. Whenever you see a lot of unstructured data and you need some structure into it, you need the data to speak to you kind of use cases, then this becomes very helpful. Yeah, like Ramana, like you're saying, the use of this comes up with a taxonomy or ontology, like however you want to define it. You can run it recursively. At the first level, it will give you like the first level of these are the clusters, these are the cluster names and everything. But you can keep running it recursively within each cluster to come up with an ontology as well. I have found that with the current capabilities of LLMs and everything, going up until 2 levels is like very accurate. After that, it starts losing accuracy because all the documents in the same cluster are already similar. Once you go like 2 levels deeper, all the documents are already similar. So doing further clustering and everything doesn't lead to much benefit. But yeah, it can help you create like 2 level or even 3 level ontologies and taxonomies automatically. Yeah, Devasi, I see that you have raised your hand. Any questions, anything? Okay, then I think thank you everyone for joining the session, and yeah, I think that and that will be all. And yeah, feel free to connect later on in LinkedIn or anything, just in case you have any further questions. I'll be happy to take them. And yeah, just thank you for joining. Thank you for your time in the today morning, and have a good rest of your day. Bye bye.